Hi, I'm Carlton Coffrin. In this video, I'll give an archive of a presentation that I gave at the PES General Meeting in 2019 as the chair of the Task Force on Benchmarks for Validation of Emerging Power System Algorithms. The talk covered a brief introduction, announcements of recent developments in this area, a progress report of what's been going on in the task force over the past year, a review of the PGlib OPF final report, and then a proposal for two new repositories, one on unit commitment and one on optimal power flow with HVDC lines. I began this talk with a brief introduction, but for the purposes of this online archive, there's no need to review that material. It's already available as videos online, so I would direct you, if you're not familiar with this task force efforts, to these previous videos that discuss what the main goals are and how it differs from some other test case efforts going on in IEEE PES. So let's begin with announcements. There have been some recent developments in the past year regarding data sets. The first one is the release of two open access grid repositories that came out of the ARP eGrid data program. That's bettergrids.org and egriddata.org. Both contain a variety of information that may be very useful to validation and benchmarking of different types of algorithms. There is also an update to the RTS96 network that has been proposed called RTS-GMLC, which has a bunch of additional data and is very well curated, so that's a great network to think about if you're trying to do these types of efforts. It's also important to recognize the grid optimization competition, which was launched by ARPA-E in 2019. It has over $4 million in prizes for developing SCOPF algorithms. But what is interesting and relevant to this particular task force efforts is that a lot of new test cases have been developed as part of this competition. So you can go to this gocompetition.energy.gov and find more than 21 publicly released networks ranging from 500 to 10,000 buses, tens of scenarios. There's many, many more that are available. And they're validated by 20 plus competitors as part of the competition. So these represent very high quality network data sets that are feasible and quite reasonable for benchmarking. So anyone who's interested in benchmarking, I would encourage to follow the grid optimization competition efforts, because as it evolves, more and more data sets will be available for benchmarking. Secondly, curators for the task force efforts are always welcome. I would love to see more benchmark curators engaging and preparing test cases on problems that are of interest to their particular research. If you would like to become a curator, it happens in 3 easy steps. You need to write a mathematical specification of the problem you want to solve, encode that problem in a standard data format, and then get your collection approved by this task force at the general meeting. Some problems I think are particularly pressing for benchmarks would be things like stochastic optimal power flow, 3-phase optimal power flow, and security constrained optimal power flow. So if anyone is interested in working on that, please contact me and I would be very happy to work with you. Now we'll move on to a progress report of the task force efforts in the past year. So in the 2018 to 2019 timeline, we have some statistics for the PGlib OPF. We have approximately 12 watchers, which is 4 more than last year, 36 stars, which is 25 more than last year, and 14 forks, which is 5 more than last year. All of these suggest the adoption of the archive as a useful resource for the community, so that's very exciting. You can see here what the window of 2-week unique visitors and views of the repository is, and it's up at least 50% from last year, so that's very exciting. The big effort in the past year was developing a comprehensive report about the PGlib OPF test cases. It has now been released and is available on archive, so you can get it there. It's approximately 17 pages long, includes 100 plus references and 20 contributors from many institutions. So this has been, I believe, a great success, bringing the community together and building a collection of benchmarks that everyone believes are interesting and valuable. Over the past year, we did routine maintenance on the PGlib OPF archive. In August, we added 8 new networks from the grid data efforts, which preceded the grid optimization competition. We did minor maintenance. There's a number of issues on GitHub where you can look at very specific things that were resolved, and we did a little bit of additional maintenance on generator bounds later in the year. So just regular updates and management of the data, so it's still a valuable and accurate resource for everyone to use. In the past couple months, our efforts have focused on the reports. So we finalized the PGLib OPF report in July. We prepared the PGLib unit commitment repository, which we'll discuss later in this meeting, and also the OPF repository with HVDC lines. Let's talk a little bit about plans for the next year. The proposed activities are maintenance of the PGLib OPF repository, and especially adding networks from the grid optimization competition. There's many networks and very large networks coming out of that competition, which could be a great benefit to this archive. We also plan to release this unit commitment repository, and over the next year we'll explore the curation of more difficult cases and the best known solutions for the cases that are already available. We're planning to release the OPF repository with HVDC lines. It currently does not have a large number of networks, so we will propose to curate additional test cases in the next year. So we'll begin with an overview of the unit commitment proposal, moving on from our optimal power flow library, which is kind of well established, and talk about this particular proposal for a unit commitment benchmark library. First, let me tell you a little bit about the authors. It's an effort that's led by Sandia National Laboratories, J.P. Watson, and this team has had a long track record in solving unit commitment problems working with industry. This goes back to the ARPA-E nodes and Genie projects and also the GMLC program. Ben is a staff scientist at Sandia, and he did his PhD on the foundational mathematics of unit commitment problems. If you would like to see a very detailed study, he has this technical report which compares many formulations and discusses some of the challenges and how you formulate the problem. So both of them have joined up and have proposed a benchmark library for unit commitment, which they feel reflects the most big challenges that are facing industry today. What are some of the key features of the formulation they propose? There's many different types of unit commitment formulation. This particular formulation focuses on the commitment of a generation fleet to a projected demand. So it's a deterministic, no network unit commitment formulation. It has lots of temporal constraints, ramp rates, and up and down times, and that presents one of the bigger challenges. So it has a natural encoding as a mixed integer linear program. There's no nonlinear equations like in the AC power flow problem. And each instance requires approximately 24 parameters. There's 9 different types of variables and 23 constraints. So it's not a very simple mathematical program, but we've tried to hit a balance of simplicity and accuracy with respect to industry practices. So there's a model formulation as part of the documentation. The math is written very small here on the side. I'll try to summarize it in some of the key features. So you have spinning reserve requirements. You have renewable generation, which can only be curtailed. You have ramp rates, min, up, and down times for generators. Variable off-time startup costs. So if you've been off for a short amount of time, it's cheaper to start up than if you've been off for a long period of time. No load costs and piecewise linear convex functions represent the generator cost functions. And there's a consistent time step of 1 hour, which is very typical in current market operations. In terms of a data format, we did not find that there was a suitable established format for this type of instance of the unit commitment problem. So a JSON-based format was developed because it's easy to parse with cross-language support, and it's pretty much one-to-one with the mathematical document. So if you can understand the LaTeX document of describing what the unit commitment formulation is, it should be fairly easy to read the JSON file and then build up that problem in a mathematical modeling language. As part of that, we've also developed 2 reference implementations, one in Pyomo for Python users and another one in Julia and Jump for Julia users, and both are producing the exact same results under the same circumstance. So it's a good validation the data sets are meaningful and the implementations match the mathematical formulation. As a first release of this data set, of this repository, there are a number of data sets proposed. 12 cases based on this RTS GMLC, which have 73 generators in the fleet. Then we have 20 cases that are based on California ISO, which has 610 generators, and 24 cases based on public FERC data with 978 generators. All of these include 48-hour time periods to solve against. So quite a significant number of cases. We have over 50, and of varying degrees of difficulty, starting with a very simple case of 73 generators and going up to much more realistic sized test cases. So at this point, there was a discussion in the room of the task force if there were any major concerns about approving this benchmark library for the unit commitment problem. And there was no major concerns, although there was a discussion about the need to combine optimal power flow with unit commitment so you can solve like a network constrained version of the unit commitment problem. So that is a good point for future work, and the RTS GMLC network provides a good basis for that. But additional data would definitely be required to do this level of unit commitment with network constraints as well. In the end, this was approved without much concern. The second topic was the ACOPF benchmark library with HVDC lines. Let's start with a bit about the authors. Primarily, this comes out of the KU-Leuven and Energyville research collaboration, which is a world-leading group in HVDC hardware and modeling. They have established for some time now a tool, an extension of MatPower called MAT-AC/DC, which has been used for modeling HVDC lines in transmission systems for some time. The primary driver of this particular effort is Hakan, and he has a PhD in HVDC modeling in transmission systems. So what are some of the key formulations? The key objective here is optimization of HVDC lines during operations, not necessarily network design or installation. And so it includes a detailed and flexible model of these HVDC links in the network. There's a converter, a harmonic filter, quadratic losses, active and reactive set points, and then you can have DC buses with a mesh DC grid. So it's a very flexible model of a hybrid AC-DC system. It's not just single two-terminal point-to-point DC lines. There is a mathematical reference formulation which has been peer-reviewed and accepted into transactions on power systems. And the math is on the right-hand side here, but I would refer you to the report for the details. The key new thing here is that there's a second set of power flow equations, all for the DC network, and then the linkages between them. And they engage in the original optimal power flow formulation through the power balance constraint. Data is provided in what we're calling the extended MatPower format, so the whole system uses the same data that is in the MatPower format for AC networks, but then adds additional data for DC, HVDC lines. The details of the format are in this MAT AC/DC manual, and in theory the data should be compatible with MatPower and MAT AC/DC, as well as this Power Models extension, which Hakan has developed, called Power Models AC/DC, which is a Julia-based implementation of the same model. So again, cross-validation in two languages is always a good thing to show the data sets are useful and meaningful. So in this case, 4 networks were proposed of varying sizes. You have a 5 AC bus, 3 DC bus network as kind of a toy network, scaling up to a fairly realistic size network based on the Polish system, with 3,000 nodes and 5 DC buses. Again, this isn't a great set for doing benchmarking because there isn't enough number of cases, but we expect more to come in the following year. So at this point in the meeting, we discussed as a group this pglib OPF with HVDC lines repository, and there were no significant objections, so it was approved to become an official benchmark library. With that, we concluded the meeting, and everything went forward as planned. I'll see you again in 1 year.